Fill your summer with the sun-kissed sweetness of Amigos Refreshers. There's strawberry acai, blueberry dragon fruit, and mango passion fruit, each a tropical delight. So skip the hot coffee and amp up your day with the plant-based natural caffeine and fruity flavor fusions in an Amigos Refresher. These cool thirst quenchers are just $3.99, or there's a mega 32-ounce size for $4.99. Recharge with the bold, fresh flavor of an energizing refresher at Amigos.
When it comes to weight loss, no two people are the same. That's why Noom builds personalized plans based on your unique psychology and biology. Take Brittany. After years of unsustainable diets, Noom helped her lose 20 pounds and keep it off.
I was definitely in a yo-yo cycle for years of just losing weight, gaining weight, and it was exhausting.
And Stephanie. She's a former D1 athlete who knew she couldn't outtrain her diet, and she lost 38 pounds.
My relationship to food before Noom was never consistent.
And Evan, he can't stand salads, but he still lost 50 pounds with Noom.
I never really was a salad guy. That's just not who I am. Even through the pickiness, Noom taught me that building better habits builds a healthier lifestyle. I'm not doing this to get to a number. I'm doing this to feel better.
Get your personalized plan today at Noom.com. Real Noom users compensated to provide their story. In 4 weeks, the typical Noom user can expect to lose 1 to 2 pounds per week. Individual results may vary.
This episode is distributed under a Creative Commons Attribution Share-alike 4.0 international license. For more information, visit creativecommons.org. Mathematics is full of all sorts of objects that can be difficult to comprehend. For example, if we take a slip of paper and glue it to itself, we can get a ring. If we turn it a half turn before gluing it to ourselves, we could get what's called a Möbius strip, which has only one side twice the length of the paper. If we try to glue the edges of the Möbius strip to each other and make a tube, you'll run into trouble in 3 dimensions because this object that this would make is called a Klein flask and can only exist in 4 dimensions. These are the type of objects that we're talking about. So what is a fiber? What can fiber bundles teach us about higher dimensional objects? And what is the Hopf vibration? All this and more on this episode of Breaking Math. Episode 59, a good source of fibers. I'm Sophia.
And I'm Meryl.
And you're listening to Breaking Math. Today we're going to be talking about fibers, but before I talk to you about that, I'm going to talk to you about our plugs. If you want to get the poster, it's a cool poster, 24 by 36 inches, so it's a pretty big poster. It's matte, it's about tensors, which are like higher dimensional vectors kind of, and also derivatives, and also they're cool. We talk about Einstein's general theory of relativity on the poster, and it's generally pretty cool. Get it for your nerdy friends. They can put it on their walls, your professors, whatever. If you want to buy that poster, you could buy it on Facebook for $19.65. That's $15.15 pi to the e dollars plus $4.50 shipping and handling. If you want to donate to us monthly, for $1 a month, you can have our outlines and our episodes without ads in them. If you also donate about $23, you can get the poster there, just as like a thank you. You can also find updates about this show on Facebook, on Twitter at BreakingMathPod, our website, breakingmathpodcast.app, and you can email us at breakingmathpodcast@gmail.com with ideas, comments, questions, and corrections. And also check out our sister podcast, Touring Rabbit Holes, and they're on YouTube. So today we're going to be studying fiber bundles, right?
Yeah.
So let's just give an overview of what we're going to be doing in this episode. We're going to give the motivation for studying fiber bundles. We're going to talk about some necessary concepts like maps, homeomorphisms, and how they relate to the meat of the episode, fiber bundles. And we're going to talk about what you could do with fiber bundles. And then finally, at the end, we're going to talk about a really cool fiber bundle application called the Hopf vibration. So, Meryl, what do you think about fiber bundles?
So fiber bundles are pretty much just a way of describing these complex, sometimes higher dimensional shapes in terms of products of lower dimensional shapes.
So what is a product of a space, for example? What would that be like?
So if you have a space A, or just a set A and a set B, then if you take a point from set A and a point from set B, and you put them together, then, so that's a coordinate, right? And
yeah.
So what the product is, it's the set of all of those coordinates together.
Yeah, and so like for example, the product of the real line, which is all numbers from negative infinity to infinity, pretty much. I mean, sometimes it doesn't include those two. With itself is the two-dimensional plane, right?
Yeah, the Cartesian plane.
And it has that's right because it has two coordinates. So yeah, let's before we start getting too into fiber bundles, let's dive in. So before you already mentioned that you could study complicated objects in terms of simpler ones with fiber bundles, right?
Yeah, and so an example of that is, so one of topologists' favorite things to talk about is the Möbius strip. And if you've ever been friends with a topologist, then they've taken you like over to their place after grabbing drinks, and they'll grab a piece of paper, and so they'll take this strip, they'll twist it in half, and then put it back together and show how you can draw a line on one side of it, and then it'll go to the other side, and both sides are the same size, and that's the Möbius strip.
Yeah, and it's a kind of a cool thing because like I've heard that Möbius strips have been used as like conveyor belts in some applications and stuff. But more to the point though, they're just like really cool mathematical objects, but they're a little elusive to study, right? Like how do we model these? And fiber bundles seem to give us a way of doing that.
Yeah, because so you'll notice the Möbius strip, it has a half twist in it, but you could also glue those ends of that piece of paper together such that it just makes a ring, a cylinder. So clearly there's some sort of difference, and what we're exploring with fiber bundles is what that difference really is.
Yeah, and in a somewhat interestingly, we seem to have to reduce a Klein Möbius strip to a cylinder, and a Klein flask, for example, to a donut, but or a torus. But we're going to talk about that in the next few sections. All right, so we got to start with the concept of a set. So what is a set? A set can be like, name some nouns.
Yeah, so it's just a collection of things. So let's say that we had a set of fruits. We could have apple, pear, grape, orange, and that's a set of fruits.
Yeah, and also you could have the set of all possible oranges, right?
Yeah.
Which would be every orange that could possibly be made. So it's basic, and the way that we think about sets often is by belonging, right?
Yeah, so we could say, for instance, that grape belongs to the set fruits.
Yeah, and fruits could be a subset of foods or vegetables even. I mean, not vegetables, fruits. Although vegetables is not a botanical term, apparently. So this is basically what a set is. So the real numbers, they're a set, right?
Yeah, and so we can say that any number on the real line, let's say pi, belongs to the reals.
Yeah, and it's something that you can belong to, a set of things or a consistent set of things. And there are rules that you have to follow with this. Like with naive set theory, we get things like paradoxes, like for example, the set of all sets that don't contain themselves both contains itself and doesn't contain itself. So obviously we can't just go crazy with it. But for what we're talking about today, sets are pretty well defined. We're going to be talking about mostly sets of continuous things. So we're going to be talking about sets that are called manifolds. So since we're going to be talking about it quite a bit, Meryl, can you tell us what a manifold is?
So manifold is a particular kind of set that locally represents Euclidean space. So let's say that we have a two-dimensional manifold. This could be something like a sphere or a torus or even a Klein bottle or a Möbius strip. And so if you take any particular point on the set, then what you can do is you can map it to, I mentioned the product of the real numbers with itself, so you can map it to two-dimensional real space.
And a familiar example of a manifold might be just the space that we live in every day. I mean, at the large scale, it's largely non-Euclidean, right? But folded time and all that. But we exist in the manifold that we could consider it 3 dimensions, really.
Yeah, so we call this locally Euclidean. And that just means that locally this looks like Euclidean space. So locally, what that means is, so we look around us, we can call that a neighborhood. And in that neighborhood around us, we see 3-dimensional space. So the product of the real numbers with itself 3 times.
Yeah, because like we said, the product of if we have the set red and blue, and then we have the set apple and orange, then if we take the product, then we'll get another set which contains the pairs red orange, red apple, blue orange, blue apple. So if you think about it, the set that is all the real numbers the product of the real numbers with themselves would have every combination of 2 real numbers. Take another product and it's every combination of 3 real numbers. And this can be done more and more to get into whatever space you want. And we use sometimes a notation. It's like an R with like a 2 lines instead of 1 vertical line, and then a number like an exponent saying how many times.
Yeah, so we actually have a name for, so like that R with a line drawn through it. It's actually called blackboard bold.
Oh, cool. Yeah, so it's a blackboard bolded R with an exponent of the space that you're talking about. And if you want to talk about a general idea of space, you could use a variable there like n or nu or whatever.
Yeah, so we use like R for the reals, Q for the quotients. And also, if any of you out there are using LaTeX, then you can, write this as \mathbb.
Yeah, and LaTeX is I'm going to pronounce it the nerdy way, is a typesetting system that we used in our first paper that's on the site. We have not gotten to doing any of the other papers, but hopefully that'll change. But anyway, now that we have the idea of a set, let's talk about what a map is.
So a map, the simplest way to think of it is that you take an element of one set and you map it to another element in another set. So you take in a thing, you get out a thing in another set.
Yeah, so like for example, let's say everyone has a favorite food, right? The set that everyone's favorite food belongs to would belong to the set of foods, right?
Yeah.
So a map from the set of people to the set of foods could describe everyone's favorite food or their least favorite food or whatever.
Yeah, so like for example, this map would take, let's say I put myself into the map, and so the output of this map would be, let's say, steak.
Yeah, and so let's call this function f. So f of Merrill is steak, where f is the function that gives your favorite food. So let's say we have a map from the real numbers to the real numbers, right? We could do something as simple as doubling things, right? So we take all the real numbers and we double them. So we have a real number 2, and that maps to 4. 13 maps to 26, etc.
Pi maps to 2 pi.
It maps to tau, actually.
Joke's on you, my birthday's tau day.
I think the joke is on people who use pi. There's a debate in math where 2 pi is written as tau, and it makes certain trigonometric stuff a lot less annoying to deal with. You don't have to constantly divide by 2. But we might do an episode about tau actually sometime. But we're going to talk about maps a little more. So what's the difference between a function and a map?
So a function is a type of map. So we put a few restrictions on it. A map can map an object to any number. So a map can take something as an input and give you any number of outputs. A function puts a few restrictions on that. For one thing, we have that let's say we have a function f from a to b. Then we know that this is well defined, which means that f takes in anything in a. So its input is the whole set of a, and we know that for any item in a that we have exactly one output in b.
Yeah, and so from this definition, we don't know that everything in b can be reached, right? Let's say everybody's favorite food is steak, right? Let's say, so we have the set of all the foods, but then in this function, it would only map to steak, right?
Yeah, and so let's say that there was some food that was nobody's favorite food.
Yeah.
What is nobody's favorite food?
Yeah, pretty much everything could be somebody's favorite food. Like, I was trying to think liverwurst sandwiches.
Let's just pretend that nobody's favorite food is liverwurst sandwiches.
Yeah, okay.
So we can also have that there is something in B, the set of foods, that is nothing in A maps to it.
Yeah, and if we're doing functions that are like one example of this is a sine function, right? The sine function is a function that that if you go around a circle, it tells you and the circle is centered at 0. So if you go around the circle and you go around the point 0, 0, this tells you the height. So, and it only goes from -1 to 1, right? So there's plenty of numbers in the reals that it doesn't map to.
Yeah, exactly.
So we have different properties that we could talk about with functions. We have injectivity, surjectivity, and bijectivity, right?
Yeah, also known as one-to-one onto, or bijective would be one-to-one and onto.
Yeah, so and a lot of times I see that called bijective because it's the only one that isn't kind of like confusing in terminology. So injective functions are one-to-one functions. Do you want to describe these?
So a one-to-one or injective function is a function that, so for any two things in our set, let's say set A is the set of people in a town, and set B is everyone's bank account number, and we'll just assume there's no joint accounts, everyone has their own bank account, then if you have any two people in the town and they're not the same person, they'll have different bank account numbers.
Yeah, so if you see two bank account numbers that are different, you know that the people associated with them are different people.
Yeah, or if you get two bank account numbers and next to each other you see they're the same number, they belong to the same one person. So the logical way of saying this is, so let's say that we have x and y in the set A, and we have a function f. Then f is injective if for a different x and y, we have different f of x and f of y.
Yeah, that makes sense. And so now we want to talk about surjective or onto maps. So surjective maps map at least one thing for everything that they can be mapped to. So let's say we have a map of people to addresses, right?
Yeah, so let's just assume that we have a town where there are no vacant homes. Then, so what we have is that, so we can have that for every address in the town, there's a person who lives at that address.
Yeah, and multiple. And let's say people like live in the same house, right? If they cohabitate, then there are multiple people. If you have one address, you might have the same address for two different people. So that means it's not one-to-one, right?
Right. So one-to-one and onto don't necessarily mean each other. And so what we mean by onto or surjective is that, so for everything in a set B, so let's say that we have just a set B, a set A, and a function f, then for every y in set B, we have some x in A such that f of x equals y.
Yeah, so if a function is a one-to-one but not onto, we can think about the bank accounts example, right? So everybody in the town obviously has a bank account number, or because we're gonna, or at least we're only considering the people who have bank account numbers,
We'll
right?
assume that's the case, that everyone has a bank account number.
Yeah.
And it's a different account.
Yeah, but if you've seen bank account numbers, they're like 10, 20, whatever digits long, right?
Yeah, so there might be some bank account numbers that aren't used.
Yeah.
So not every bank account number has a person associated with it. So it's not onto.
Yeah, whereas the house is, every house has at least one person living in it. So a bijective function is something that is both surjective and injective.
Or both onto and one-to-one.
Yeah.
So let's say that there's a classroom where there's 30 people in the class and there's 30 seats.
Right.
Yeah, so a bijective function would be that every person has their own seat, and for every seat in the classroom, there's a person in it. And so what's cool about a bijective function is that you can say that it's injective or surjective both ways.
Oh yeah, right. You're meaning like if you take the inverse of the function, which reverses the way that it goes. Well, bijective function, first of all, can be inverted, right?
Yeah, and the inverse of that function is also bijective.
Yeah, which is pretty cool. And finally, let's talk about the pre-image of something.
So first we'll talk about, I guess, what an image is. So let's say that we have the set A, and so we'll call the image f of A. So what this is it's the collection of all sets in B such that there's an x in A, such that f of x is in that set.
So basically, you just take a collection, right, of a certain amount of points, or like elements from the set that is mapping from, right, and then you apply the map to all of them, and then you collect them, right?
Yeah, and so that's an image. So a pre-image then is sort of going the other way, and it's, let's say that we have a point B in Y. So we can have a whole set of elements we call A that F maps over to B. And so that whole set of elements X is called the preimage.
So that's basically what we're going to talk about, maps and functions. All right, so you want to describe fibers?
Yeah, so we're going back to our idea of maps and functions. So what I want to say is that we have two manifolds. Let's say that one is in 2 dimensions, the other is in 1. The most basic definition of a fiber is that it's the preimage of a function at a particular point.
Yeah, and so let's break this down a little bit. All right, so now we're going to talk about fiber bundles, and before we talk about that, we're going to have to talk about what fibers are. So let's say we have an infinitely large cylinder, right? That's infinitely long. You could describe a point on the cylinder in terms of the angle of it is from the center. So we could call a certain point on the cylinder, we could say that that's 0 angle. And we could say that that is 0 distance too. Because, right, if we have a point on the cylinder, we could describe it in terms of how far it is down the cylinder and then how much we have to go around the cylinder to get to that point, right?
Right.
And so if we take a function that takes a cylinder, that takes a point on the cylinder, and remember that's described in terms of the angle and the distance, and we take that and we map it to just the angle, we're on our way to describing a fiber.
Yeah, because what'll happen is, so let's say that we map a cylinder to a circle. Let's say that we do that by saying however far around this point is on the cylinder is how far around it'll be on the circle. And then, so let's call that map pi for projection. Then, so let's talk about what pi inverse of this point on the circle will be. So it won't just be a single point on the cylinder, will it?
No.
Yeah, so it'll be every point on a line that is that angle on the cylinder.
Yeah, so it would be a point that goes like straight down the cylinder, right?
Yeah, it'll be a straight line on the cylinder.
And that straight line that goes from negative infinity to infinity, or however long the cylinder is, would be a fiber. And we could also reverse the way that we're talking about fiber bundles in this cylinder example because it's so simple, right? Like, for example, we could have the line, we could draw an arbitrary line that goes down the cylinder, and we can map points on the cylinder because remember we're describing them in terms of distance and angle. We could map that to just distance. And then in this case, our fibers would be the little circles that go around the cylinder at any given point.
Right, and in this particular case, either example works.
So how do we use fibers to construct?
Saving money on everything for your next project at Menards. It doesn't matter what job you're up against. Works, cordless power tools, and lawn equipment have the power for you to get the job done faster and easier. The PowerShare 20-volt batteries run longer on a single charge, and they can be used with other tools. Check out Menards' entire selection of Works, cordless power tools, and lawn equipment. Plus the weekly flyer today on Menards.com.
Save big money at Menards.
Fiber bundles. Like, what is the difference between a fiber and a fiber bundle?
So a fiber bundle is described as, so you have 4 things that make up a fiber bundle. The first is our total space. So that's pretty much the space that we're working with.
So it's a complex object, right, that we want to simplify.
Yeah, and we'll call that E. So we have that we are breaking it down into 2 things, a base space and a fiber.
Yeah, and so before in our cylinder example, so let's go with the first example. We can imagine the total space as the surface of the cylinder, right?
Yeah, so E is the cylinder.
And the base space, it's just an arbitrary kind of circle that goes around, that can be mapped to around the cylinder, right? And so the base space goes from 0 to 2 pi, because that's one rotation of a circle. A lot of times people use degrees, but 2 pi or tau.
Yeah, and then so let's think, because this is an infinitely long cylinder, that means that we have that one of our coordinates is that point on the circle, and then so we still have something left, and that's the fiber, which would be our copy of the real line from negative infinity to infinity, and that's our other coordinate.
Yeah, and the projection is basically takes the distance and the angle and spits out just the angle. And the angle is from negative infinity to infinity, right? So it is a part of the fiber. Because remember, the fiber is the preimage. So if the projection maps everything to this singular ring, then the fiber at a certain point on the ring is every point on the cylinder that maps to that point on the ring.
Yeah, and something important to know about fiber bundles is that every single fiber is the same. So we're saying that for every point on the circle, we have an entire copy of our fiber of this real line, negative infinity to infinity. And so together, we get that those things are called a product space. And because our total space, E, is the same thing as our product space, which is a product of our base and our fiber, we get that this is called a trivial fiber bundle.
Yeah, and so the product space. Remember, we took out the angle with our projection, right? We're kind of putting the angle back in by multiplying the two sets, taking the product of them. Because remember, the product of the real line with itself is anywhere on on the 2-dimensional plane, right?
Exactly.
And remember, the base space is lower dimensional than what we had before. We go from a higher dimensional space to a lower dimensional space. And that it's apparent on the ring, right? Because an angle around the ring, that's only one number, versus a coordinate on the tube that requires two dimensions to describe well.
Yeah, makes sense.
And I mean, of course, you can have space filling curves and stuff, but those are not continuous when you move smoothly. And we talked about that on a previous episode if you'd like to go listen to that. So what's some examples of some fiber bundles? And we might be using the term fibration, but technically a fiber bundle is a type of fibration, but not the other way around. But we're just going to use them interchangeably for this podcast only.
Yeah, so, and if in case you're wondering, a fibration is just a generalization of a fiber bundle where not all the fibers necessarily have to be identical.
So what is the trivial fibration?
Yeah, so, and we'll just call it the trivial fiber bundle. So it's kind of like we talked about with the cylinder. So we'll have 4 things again: E, the total space; B, the base; F, the fiber; and pi, the projection. So what this is that it's a fiber bundle where, because pi is what projects the E down to be the base, and then so what'll happen is that we'll have, for every point on the base, we'll have a fiber, and so the product between the base and the fiber will be homeomorphic, or it'll be the same space as the total space itself.
Yeah, so these are fiber bundles that don't really require fiber bundles, right?
Yeah, they're about the simplest objects that could possibly use those sets of parameters that they do.
Yeah, and I mean another one might be like a line in 2D space and the lines, and then take the shortest distance between any point on the 2D space and the line, and that'd be another trivial fibration, right?
Exactly.
But then we have things like the Möbius strip, where the Möbius strip. Do you want to describe that in terms of fibers?
Yeah, so just like the cylinder, so if we draw a line at the middle of the Möbius strip and we just keep going and looping around, then eventually we'll still loop back to ourselves. So we still have a circle in one-dimensional space. So we're going to call this circle at the center of the Möbius strip our base space.
Yeah, and so if you're on the Möbius strip, right, you have this line now going through the middle of it. And so you could say that if you have another point somewhere else on the Möbius strip, the point that is the shortest distance between any point and that point, or like basically the line that goes parallel to it, is one fiber, right? I mean perpendicular to it, right?
Yeah, so, and what we'll say is that for any point on the Möbius strip, that the projection from our Möbius strip to our base space, the circle, is wherever along that middle line the circle, that point is.
Yeah, so now if you take the product of the base space and the fibers, remember each fiber is a line segment. We can say it goes from -1 to 1, right? And we can say the base space is like a circle, so it goes to 0 to 2 pi. So the product of those two turns out to be a cylinder, which is not homeomorphic to a Möbius strip, right?
Yeah.
So before we continue talking about the Möbius strip and what we can do with it, let's talk about trivializations. So what is a trivialization? What does that term mean?
So we know that we have trivial fiber bundles, and that means we don't have to do anything to explain how the total space is related to our product space. But for something with the Möbius strip, where we get a product space that is the cylinder, clearly we have to do something to explain how that works. So we look at our base space, we take a point on it, and we take a neighborhood around that point.
And a neighborhood is like all the points that are like kind of like glued and immediate. Like if you take a point and let's say you have like an inky pen and like the surface that we're drawing on is really fibrous, and you just kind of touch it and let the ink roll out, then that ink will be a neighborhood, right?
Yeah, and so for any neighborhood, just like for any point, you can still have a pre-image. And in this case here, so the pre-image of a neighborhood on the circle will be a slice of the Möbius strip.
Right. And since the space that we're dealing with is the base space, which is a circle times a line segment, right, that it almost locally looks like a cylinder. It seems like that's the power of this.
Yeah, and so a slice of the Möbius strip looks like, or is even homeomorphic to, the slice of a cylinder is what's important here.
Yeah, and I think you could kind of imagine this as like, let's say you have a cylinder and it has some like drawings on it or something, and you turn it around 180 degrees and you see more drawings. You keep turning around so it's a full circle, and all of a sudden you start seeing the same things upside down, and then only once you turn it around twice do you get back to the same place.
Yeah, and so I think at this point I can safely say what a trivialization is. And so if we take a set of neighborhoods that cover our base space, then so their pre-images will cover the total space. And at that point, for every neighborhood, we can have a homeomorphism between the pre-image, the slice of that Möbius strip, and the slice on the cylinder.
Right, and this is like some kind of imaginary cylinder,
Yeah.
obviously. It's like if we were a tiny ant crawling along this Möbius strip, kind of basically in 2 dimensions. If we were a completely flat little ant, right, we go around the Möbius strip and it looks pretty much like a cylinder to us locally, right?
Yeah, so what we would see on the Möbius strip and what we would see on the cylinder would look the same. So I want to construct a trivialization for the Möbius strip now. And so the way I'll think about it is that I want 4 neighborhoods on the base space. And let's talk about those as semicircles.
And the base space, remember, is that ring that is...
It's the circle.
Yeah.
Yeah. So let's say that we have a left and right half of the circle. And then, so that covers everything except the north and south poles. So what will we do if we want to have what will we do if we want to have everything else covered?
Oh yeah, we could get another 2 semicircles and then orient them parallel, right? Perpendicular, right?
Yeah, so if we put those all together, so the union of 2 sets, we don't put copies of things in it. So the union of all 4 of these together is just the circle.
Yeah, and although each segment looks a lot like a cylinder, so you could kind of imagine this as like gluing manifolds together, right?
Yeah, and so we need to think then about what happens between a semicircle and its pre-image on the Möbius strip. So we know that this is going to be homeomorphic to some strip of the cylinder, but what we also need to think of is what's happening on the Möbius strip itself, because that tells us how the Möbius strip is different from the cylinder.
Yeah, so you almost have to be cognizant of this from the get-go, which is obviously the point, right? You're dealing with these complex objects and simplifying them. And so one thing that obviously you know about going in, so let's say we have some fiber, right? Let's say it corresponds to angle that we're calling 0. And on each side of the fiber, on each edge of the Möbius strip, in the same fiber, you have a blue eraser on the left and a red eraser on the right.
It works.
It works. So let's say these 2 drive at the same speed down the Möbius strip. They're going to continue being on the same fiber at any given point if they have the same speed because they're the same kind of eraser.
Yeah, so let's say that they're starting at one point of this semicircle on the base space. So let's think about what happens as they make it across that semicircle. So what happens is they'll make it around the Möbius strip, but the blue eraser will be where the red started and the red will be where the blue started.
And so this base space that we're talking about, it seems to almost be twice the length of a normal circle, because you go halfway around it and it's almost like going all the way around the circle. But remember that the racers now will be quote unquote on the other side.
Yeah, because the red is where blue was started and the blue is where red started.
And if these are 2-dimensional racers, you'll notice that they're flipped. If one had like a decal that said E on it and another decal that said P on it, an uppercase P, when they get back to the original point, it'll be a weird 3 and a strange Q. All right, so remember that when you go halfway around the Möbius strip, you're kind of going the quarter way around the circle. So that's just important to of the base space circle.
Yeah, so going around the base space of the circle is going around the Möbius strip all the way, but consider that halfway around the Möbius strip, you cross through the same point once, but you're facing the other way.
Yeah, it's like if you put your finger on the Möbius strip, the tip of your finger would make a circle going halfway around.
Yeah, so you go all the way around the Möbius strip, but you're facing the other way, so you haven't gone all the way around yet. You have to go around one more time before you're facing the same way. Then you've gone all the way around the Möbius strip, which means you've gone all the way around the base space, the circle.
Yeah, exactly. Yeah. So how does this relate to the Klein bottle?
So, and this is something that I think we could leave more as an exercise, but so let's think about what the Klein bottle really is. And so we're going to think about it in relation to a torus. So what is the torus? Like, what's it a product of?
The torus seems to be a product of two circles.
Yeah, so S1 cross S1, as we would write it.
Yeah, and the reason why my reasoning here is you go around the circle, and that's one circle, and then for each point on the circle, you can have like a little slice of the donut.
Yeah, and an important caveat here is that, so this doesn't work with the sphere, does it?
No, it doesn't. It seems like the sphere would be, because I mean, I could imagine like going around, like having each great circle with respect to one great circle on the sphere.
Yeah, so let's think about it this way, is that, so the sphere goes from, so you have one set of coordinates that goes around, so you could say from 0 to 2 pi, but, so you have another set, so that's from the north, you have another set of coordinates, and that goes from the North Pole to the South Pole, and so that would be from 90 degrees, or pi over 2, to negative 90, or negative pi over 2.
Oh, so it'd be a semicircle, obviously, which is a line segment.
Yeah, so it's not quite the same thing as a torus in this case.
Yeah, so yeah, that makes sense.
So what I want to leave to you, the listener, as an exercise is we talked about how to get a fiber bundle out of the Möbius strip, and how could we do that the same way, and how could we construct a trivialization with the Klein bottle such that we can get a relationship between the Klein bottle and the torus.
Yeah, and I mean, a little bit of a hint on kind of talking about what a Klein bottle is. Remember, a Klein bottle is what happens if you stitch together the edges of a Möbius strip, which can only exist in 4D because you'll get to a point where you're kind of trying to stitch into itself.
Yeah, and the way it'll look if you try to immerse it in 3 dimensions is
kind of like the shadow, right?
Yeah, it'll look like a bottle that is intersecting itself, sort of.
Yeah, you can imagine this imagine like a Chianti bottle, like a wine bottle with a wide base, and imagine the top of the bottle is extended and the tube goes into itself and then connects to the bottom and then becomes the bottom.
Yeah, in fact, there's even a limerick that I heard once that describes the Klein bottle, and it goes something like, "There once was a mathematician named Klein who found the Möbius strip divine. Said he, if you glue the edges of 2, you'll get a neat bottle like mine."
So finally, we're going to talk about a cool thing that you could do with fiber bundles, and it's a fiber bundle called the hop fibration.
Right, and of course, fibration is a generalization of fiber bundles. It just so happens the hop fibration is also a fiber bundle.
So what is a 3-sphere? We've talked about this before on a few episodes, but it's good to review.
Yeah, so we can kind of think of it as a shape in 4-dimensional space where, so we think of the sphere as, in 3-dimensional space, all of the points that are equally distant to the origin, right?
Yeah, so and so this would be called a 2-sphere, right? If it were like in 3 dimensions.
Yeah.
Because it's like a 2-dimensional skin.
Yeah, so in 4-dimensional space, we then have a 3-dimensional skin, and we call this the 3-sphere.
Yeah, and this is almost like a space. Like if you were in the space as a 3-dimensional creature, you would not know you were in it until you went in a certain direction and then got back to where you started by going in a straight line.
Right, so it's kind of similar to how if you're a flatlander on the sphere, you don't necessarily know it's a sphere.
Yeah, or like even if you're a human being on Earth, it takes until people invent astronomy until you realize you're not on a large plane. You're actually on a sphere.
Yeah, and some people would still like to argue otherwise.
So what is the Hopf fibration? So basically what it is you can imagine a three-sphere. A three-sphere would also have great circles, right? Great circles being the circles that bind the four-dimensional sphere. And it turns out that we can map each great circle on the three-sphere to a point on the two-sphere.
Yeah, so what we got then is a fiber bundle where we're thinking of the total space as the three-sphere and the base space as a two-sphere. So all that's left is then each fiber is a circle or a one-sphere.
And if you're interested, the formula for the Hopf fibration, given the 4D coordinates A, B, C, and D, is a 3D point, which is a squared plus b squared minus c squared minus d squared. The y coordinate, or the second one, is 2 times quantity AD plus BC and quantity. And the z, or the last one, is 2 times quantity BD minus AC. And if you check this out on your own, you'll see that if A, B, C, and D are, for example, the distance between them and 0, 0, 0, 0 is 1, then the point that you get here is also equidistant from 0. It is 1 as well. So what does fibration look like when it's projected into 3D?
So we can get some sort of idea of what this three-sphere looks like by using a technique called stereographic projection. We can use this to show what a three-sphere would look like in three-dimensional space, or a two-sphere in two-dimensional, or even just a one-sphere, the circle, in one-dimensional space.
Yeah, you could think of this almost like a shadow. Like a shadow takes a three-dimensional object and projects it into two-dimensional space on the wall.
Yeah, and so what kind of happens then is that, so for any point on the two-sphere, we get this whole ring of the three-sphere, and so as we move about the two-sphere, we get that these rings sort of are linked together.
Yeah, which is pretty cool, and it turns out that they fill all space.
Yeah, because the three-sphere is a whole much more complicated beast than we might think of it being just a sphere.
Yeah, it's really kind of mind-boggling to get your head around the sphere, because I mean the simplest way to really describe a three-sphere is like a balloon that you blow up and then you just kind of slow down blowing it up and then you like let it go, and over time that's a three-sphere.
Something like that, yeah. And that's assuming that a fourth dimension is time, I imagine.
Oh yeah. Yeah, I should have mentioned that. Three spheres are complicated. I mean, there is a problem that was unsolved for 102 years that we're not going to quite talk about called the Poincare conjecture. That it involves 3 spheres.
Yeah, it's a little terrifying to think about. Fiber bundles let us know what shapes are different by relating their coordinates. In this way, they're a way of interacting with tricky mathematical objects. We learned how the three-sphere can be described using a sphere of circles. Their beauty, however, can surely be said to lie in the fact that they show us both how simple space can be regarded as, while also letting know of their inherent complexities.
I'm Sophia.
And I'm Meryl.
And this has been Breaking Math. Want to support the show? Buy a poster. Facebook.com/BreakingMathPodcast. Also, Patreon, we really appreciate. Patreon patrons, $1 or more gets you the show free of ads. And we're going to start adding a few more incentives to that. So stay tuned for that.
And as always, I would like to give a shout out to the University of New Mexico Graduate Workers Union.
Awesome. And keep on breaking math and breaking, I don't know.